Alright, in this video I'm going to explain how you can use symmetry to solve certain Queen's puzzles. So let's start by looking at a puzzle that is completely symmetric. We can see that everything here on this left side mirrors exactly onto this right side. We have the same colors and we have the same regions for each color. So this puzzle has exactly two solutions. And we can see that there's sort of a left-hand side solution, like with this purple up here in the left, and a right-hand side solution that's the exact mirror of our previous solution. So because one side of the puzzle is always going to constrain the puzzle in the same way as the other side, puzzles with symmetry must always have multiple solutions or no solutions at all. And that's useful to us when we're solving puzzles that have one solution, because it lets us know that if we ever reach a point where the rest of the puzzle is symmetric, then the action we took to get there must have been incorrect, because that symmetric puzzle must have no solutions to it. So let's see how that can be applied to a specific puzzle. So this is puzzle 676. Right off the bat, we see quite a bit of symmetry, but we can also place a couple of obvious queens to start off. We see that these three are our only candidates for this column, so we can eliminate this one, and then same thing here, same thing here. And now we have, again, almost perfect rotational symmetry. Like this cell rotates through to this cell, this region rotates through to this region, being the same colors and the same shape, except for these three and these three. So we need to do something that would eliminate all of these three. So if we were to place a queen here, for example, that eliminates all of those cells. And now we see that the rest of the puzzle is perfectly rotationally symmetric. We sort of have a left-hand side or a top side here that rotates through to a right side. And they're exactly the same, meaning they must have either multiple solutions or no solutions. And because we know that this puzzle has only one solution, it can't have multiple solutions, so we know that there's no solution to the rest of this puzzle. Another way to think about it is we could again test, is this part of the solution, and then follow it all the way through until we reach a contradiction, and then do that for every cell. Eventually we'll reach a contradiction for any candidate that we test here, but we don't have to do that because we know it's symmetric, so no solutions. So we can take a step back and say that this queen must have been incorrect, and we can put an X there. And at this point, the rest of the puzzle is solvable with pretty standard logic. We only have red in this row, so we can get rid of the rest of these reds. Now we have this gray and red cluster and another gray and red cluster here. So these greens, which see those clusters, are gone. That lets us place our next queen here, and our next queen here, and then here, and let's see, here, and then here, and there we go. So that's one example. Let's look at another one. This one is a little bit more complex, but uses the same symmetry rule. Again, we can see that there isn't too much we can do. We can get rid of those ones, we can get rid of these ones, but that doesn't really help us a ton. We can see that everything is rotationally symmetric about the center, except for this cell and this cell. So we can see that if this is an X and this is an X, then the puzzle is perfectly symmetrical. If this is a queen and this is a queen, again, we have perfect symmetry. But if one is an X and one is a queen, then we have our asymmetric puzzle. So that is going to be what we're looking for. We need one of these to be a queen and one of these to be an X, meaning anything that causes both to be an X or both to be a queen can be eliminated, like this cell and this cell, which would both eliminate those. And an important note here is when we placed our test candidate here, we saw that the rest of the puzzle was perfectly symmetric. Oops. And that isn't the case here. we're eliminating our asymmetric cells, but the rest of the puzzle at this point is still asymmetric, right? Because this isn't on our line or point of symmetry. But it is important to note here that that doesn't matter, because if we place a queen here and then follow it through, whatever solution that we could reach from that, we could reach an equally symmetric solution by starting from this point, because both of them still eliminate the cells that give our puzzle its inherent asymmetry. So in a way, these two sort of act like an extra color or pair. And we can see that when this one's adjacent to this blue, this one's adjacent to this blue. So we have sort of a cluster. Like if we were to place a queen here, then we have no way to solve this, because we know this is an X, this would have to be a queen, and then we have no solution there. So anything that sees both of those clusters can get eliminated. That's going to be these ones. Then we have the same condition with this turquoise and our pair, this turquoise and our pair. So we can eliminate everything in this row and up here as well. And then we have the same condition here. We have only red in these two columns, and only our pair in these two columns, and that lets us eliminate these ones. And that's especially interesting that we're able to eliminate all of these purples, even though this cell, part of our asymmetry pair, is purple. In this case, it's sort of acting like a separate color rather than purple, but of course it is still purple, and we can use that still, seeing that this is red, purple in the same column. We have this purple and this red that both see all of these cells, so we can eliminate those. And that leaves us with another cluster of yellow and red here, a cluster of yellow and red here, so we can eliminate everything in this row. And that simplifies our grays a little bit, so we can get rid of these two. And now we only have this as our leftover red, so we can place our queen here finally. These two yellows, see both of these cells. And then we have in this row and in this column, we have contained our yellow and our gray, so everything else can go, including this purple, giving us our last purple. And that solves for this turquoise and solves for this blue. And then now we only have these two as that light orange, so we can get rid of these cells. And that gives us this queen. Then we only have these dark orange, that eliminates these, so we can place a queen here. And then this one, getting a little ahead, this one eliminates this, and then we can place our remaining queens. So those are some examples for how to use symmetry to solve these specific puzzles, but in general, you can always look for if a puzzle is almost completely rotationally or mirror symmetric, which cells prevent that puzzle from being perfectly symmetric, and then how can you eliminate all of those cells. I hope to see more puzzles like this in the future, and I'm always happy to answer more questions that people have to help understand these rules. Thanks.